Schwarzschild metric is modified. So the conventional model assumed that the Schwarzschild solution is a good approximation, meaning that if we do this, we're going to get only a small modification to the Schwarzschild metric. So it also means that the energy momentum tensor for the vacuum state around horizon is going to be small. So that's the main thing we're going to check. That's one of the main things we're going to check. So when we do this, we assume spherical symmetry. So the most general form of the metric would be like this. Here you have two parametric functions, C and R. If it's a static solution, it would only depend on the spatial coordinate R. But we are going to consider the dynamical process. So actually, it would also depend on T. C will be referred to as the conformal factor, and R as the areal radius. D omega squared is the metric for a unit sphere. So R is giving you the area of a symmetric sphere as 4 pi r squared. So a priori, this is not a one-to-one function to the radial direction. You could have larger radius and lower radius and larger radius again as you move outward along a radial direction. It tells you the area of the symmetric sphere. So it's called the areal radius. So it's not really the distance between a point and the center. Often we will use the light cone coordinates little u and little v like this. So u is the parameter, affine parameter for outgoing waves, and v is the affine parameter for ingoing waves. So for the Schwarzschild metric, this conformal factor is 1 minus a over r. A is the Schwarzschild radius, and r star is called the tortoise coordinate. It is related to the areal radius in this way. So by inverting this function, you get r as a function of r star. So this is standard. So in this talk, almost everything is standard. Nothing new. An important assumption, the main assumption we want to check is whether the horizon is uneventful or not. So we mentioned last time that if you assume equivalence principle, then for freely falling observers, they have the proper time tau, and they can have a spatial direction, a radial direction coordinate sigma, so that it is orthogonal to tau. Then in this reference frame, for freely falling observers, we expect that the energy momentum tensor of the vacuum cannot be larger than 1 over a to the 4th. Otherwise, you would say that observation made by these freely falling observers would be quite different from an observer floating in Minkowski space.
Pei-Ming,
yes.
One check here. This R star coordinate, in terms of this R star coordinate, horizon is located at R equal minus infinity, right?
That's right.
Okay.
Okay, thank you. So then you can define the light cone coordinates for the proper time for and spatial direction for the freely falling frame. And then in this coordinate system, of course, the energy momentum tensor of vacuum is also no larger than the order of 1 over a to the 4th. We will show later that this coordinate, capital U and V, is related to the little u and v defined in the previous slide for Schwarzschild coordinate at large distances in this way. So d capital U over d little u is proportional to C. D capital V over d little v is of order 1. And C, this conformal factor, we know that it's going to 0 at the event horizon for the Schwarzschild solution. For the dynamical solution, we expect that C becomes arbitrarily small, very, very small. So it means that for a little change in capital U, you have a large change in little u. So for freely falling observers, your watch only changed a little bit in reading, while people at far distance would take a very long time to see this change on your watch. So then as the energy momentum tensor is a tensor, so you use the tensor rule to determine the value of the components in this new coordinate system, little u and little v, suitable for observers at large distances. So then you see that because of this factor of C, TUU, which represents the energy flux of outgoing energy, you have very little outgoing energy flux around the horizon. This is the relation for freely falling observers crossing the horizon. Since C is going to 0, so TUU is very close to 0. Similarly, TUV is very close to 0. Only TVV, the energy flux, the ingoing energy flux, is finite, is of order 1 over a to the 4th. Now, due to energy conservation, at large distances, you see outgoing Hawking radiation take away energy of the black hole. Around the horizon, what you see is that the outgoing energy flux is 0, nearly 0, and the ingoing energy flux must be negative. So this is the main feature for the energy momentum tensor outside the collapsing matter around the horizon in the near horizon region. So this is, the first line is the result of equivalence principle. This equation in the box is something I will show below. And then the conclusion is that we have this condition. So you can take this condition as the energy condition, the condition on the vacuum energy momentum tensor for an eventful horizon. So to show that you have this d capital U over du going like C, it's a standard calculation. You just consider a freely falling particle in this background geometry. To simplify the derivation, you can consider a time-independent conformal factor because the time it takes is short. So this conformal factor would not change much. This will be clearer a little bit later if you are a little bit suspicious about this. And then since there is a translation symmetry in time, you have a conserved energy, and then it's easy to write down the proper time for freely falling observer in this way. So you have a constant mass for the freely falling particle, the constant conserved energy, and then you have this conformal factor C. So then it's straightforward to show that when this particle is crossing the horizon, if its velocity is approaching the speed of light from the viewpoint of external observers, then you do get this du over du proportional to C result. And therefore, we get this energy condition for an eventful horizon. Is there any question?
So what was the H? Could you remind me what is H?
I'm looking for H. Where
next
is H?
Page. Next page. You have a.
You mean last page?
Oh, there at the end. HR.
Oh, HR. Thank you. That's abbreviation for Hawking radiation. Sorry.
Oh, Hawking radiation.
Right. So at large distance, you see outgoing Hawking radiation. At around the horizon, you see negative Hawking radiation going inward to deduce the energy behind the horizon.
Right. So that is still, I mean, horizon scale. Okay.
Right, so this is the standard viewpoint about black hole evaporation.
Just one check again.
Yes.
Large U and large V is the coordinate for the free-falling observer.
That's right.
It's the same definition as the usual large U and large V coordinate, right? I mean, this in this coordinate system which covers inside black hole.
Yes, that's a very good question. So, in principle, I defined it differently, but I'm just about to show in the next slide that the relation is the same. So here I'm defining freely falling observers, so they have their proper time. And the tangent vector can be normalized, and then you can define another space-like normalized vector, which gives you the coordinate sigma. And then you can define capital U and capital V. So defined this way, I'm not referring to the space inside the collapsing matter. But if we consider a thin shell, this is the standard thing people do. People often consider the thin shell as the collapsing matter so that every calculation can be done more easily and conveniently. In this case, you would have...
I am asking whether this coordinate U and large V covers the region inside the horizon. Since you would like to stay outside of horizon.
Oh, no, I'm not staying outside the horizon. So here I'm in a region, sorry, I don't have the event horizon. I have the trapping horizon, and I'm considering the neighborhood both inside and outside the trapping horizon. But the trapping horizon is time-like, as I will show later. So there's nothing going, nothing preventing you from going in and out. So for a freely falling observer, they can easily cross this trapping horizon. So this capital U and V is defined everywhere. Everywhere, I mean, before you have event horizon and other stuff.
So you don't have here, you don't have a definition of event horizon, right?
No event horizon, right.
So you are, what you have here is just this local trapping horizon.
That's right. That's right. So
the trapping horizon is basically stay outside the horizon or what?
The event horizon is, if it exists, it should be around here, like where my cursor is. So the event horizon.
My question is whether the coordinate U is covering those regions or not, large U and large V.
Whether they cover the inside of the event horizon. Is that the question?
Yeah.
Okay, yeah. If you wait long enough so that the freely falling observers enters that region, then you can still define capital U and V because they are the capital U and V are the local coordinates for freely falling observers. But I'm not going to need to talk about that because I will be focusing on the early stage of evaporation before the end of the evaporation. Note that you have the event horizon only after the point where distant observers see the whole black hole disappearing, right? At the final point of evaporation, distant observers see the black hole suddenly disappear. That is when you have event horizon. I'm talking about all the time before that, well before that, when the black hole is still large for a distant observer. So that's why I'm cutting off along a light-like line. So I'm looking at this problem from the viewpoint of a distant observer. So well before the black hole evaporates completely, I have a large black hole and I have no event horizon, and then everything is smooth and fine. Is that okay? So, I mean, if you like, U and V covers the inside of the event horizon, but I'm not going to need any information about that.
Okay, okay,
I mean, of course, behind the horizon, these equations would not be valid. I mean, because little u and little v do not cover behind the event horizon. So these equations are valid only outside the event horizon, but inside the trapping horizon as well. Other questions? So people often consider the thin shell, and you have a thin shell. Its outside is approximately Schwarzschild solution. Its inside is just Minkowski space. So you can use the usual Minkowski space coordinates T and R and define Minkowski-like coordinates V and U. I'm also using capital V and U to denote these coordinates because their relation with the little u and v is going to be the same. So you can use the continuity condition for the area radius. So the area radius of the shell is denoted as capital R. So from the viewpoint of the internal space inside the shell, the area radius is actually just the radius, usual radius. So it has a certain shrinking velocity. And from the viewpoint of outside observers, it has a velocity which is like this, which is determined by this equation, the metric of the external space. So taking the ratios of these two expressions, D capital R cancels, you get also D capital U over D little u proportional to conformal factor C. So if you define capital U and V this way, according to the internal space inside the collapsing shell, you again arrive at the same condition on the vacuum energy momentum tensor. Okay, so that was how we can justify the factors of C in this coordinate transformation so that we know these vacuum energy momentum tensor are of a certain order. In particular, the outgoing energy flux is almost zero around the horizon, and the ingoing energy flux is negative. But that was just the result according to equivalence principle. People also try to do a computation directly without quoting equivalence principle directly. So one such work in the early days was a paper by Davis, Voll, and Enru. They considered a two-dimensional model. So you can think of S-wave reduction of the four-dimensional space to two-dimensional space and consider a two-dimensional massless scalar field. And then you know what is the trace anomaly, and you know that energy momentum tensor has to be conserved according to the semi-classical Einstein equation. So you have two equations. You have enough equations to actually completely solve the energy momentum tensor of vacuum in this way, where C is this conformal factor. You are left only with the degrees of freedom of a boundary condition. So for the outgoing energy density of the vacuum energy momentum tensor, you have a free function which depends only on U but not on V. Now the conformal factor we usually use is a modification of the Schwarzschild metric. So it goes to 1 at large distances, so that this derivative goes to 0. So is this one. And therefore, at large distances, this is the energy flux, outgoing energy flux. This is the ingoing energy flux at large distances. So basically, these two functions, f and f bar, are going to be determined by the boundary condition. Another way to look at this is that they are determined by initial conditions. They are determined by the quantum state. You can think of it this way. So upon a coordinate transformation, say u goes to u prime, which is function of u only because you still want u prime to be Lie-Kong coordinate. Then you see that f transforms by Schwarzian derivative. And so if you take, say, coordinates capital U and V as the affine parameter defined on the infinite past, where the vacuum energy momentum tensor is that of the Minkowski space, so they should vanish, then you see that you can derive this function f from your knowledge about the relation between the coordinate of the infinite past and the coordinate of the infinite future. Now, again, I use the same notation capital U here because the Minkowski of the infinite past is going to stay Minkowski inside the shell. So it's the same coordinate system. So in this way, people can compute the vacuum energy momentum tensor and check that indeed the result agrees with the what we said earlier according to the equivalence principle. So you get an eventful horizon in this sense. Now, in this work, they assumed the 0th order approximation as the Schwarzschild background. Of course, people would suspect that this is not correct because you are supposed to have a time-dependent energy for the black hole, but you can consider approximation within a short period of time. So basically, this is saying that if you assume Schwarzschild metric approximation within a sufficiently short period of time, then it's consistent to have an eventful horizon, to have vacuum energy momentum tensor to give you an almost zero outgoing energy flux around the horizon.
Excuse me?
Yes?
So what is this delta t?
Sorry?
Sorry, what is delta t? You
Delta
discussed
t?
In the previous page. No, sorry, not this page, but where it was. So you said some good approximation for the static.
Yeah, delta little t, right.
Yes.
Yeah, so this is the time, period of time over which we use this metric as a good approximation. So the complete evaporation time is of order a cubed over Planck length squared. So if the time period of time is much, much shorter than that, then the black hole is only evaporated, say, 1% of its mass. Then then use this metric as a good approximation.
So you mean compare with this lifetime of black hole, it would be good.
That's right. However, we should also comment that what we did was the so-called en-route vacuum. So this is the vacuum defined, you can say it's the vacuum defined in the infinite past when all the collapsing matter are still scattered around a huge area so that the space is essentially Minkowski space. So we start with the Minkowski vacuum and wait for the collapse. And then the Minkowski vacuum would turn into the quantum state at the time of black hole formation. So that is the quantum state we refer to as the en-route vacuum. It is also the quantum state for freely falling observers to feel nothing around the horizon. On the other hand, you can also consider different quantum states like the Boole vacuum or the Hartle-Hawking vacuum. they have different boundary conditions. So the unruled vacuum has the boundary condition that you have outgoing energy flux corresponding to Hawking radiation. You have no ingoing energy flux at large distances. But the Boole vacuum assumes no energy outgoing or ingoing at large distances. And Hartle-Hawking vacuum assumes a balanced ingoing and outgoing energy flux at large distances. For all the other vacuum states, except the unruled vacuum, you are actually going to get large corrections around the horizon. The uneventful horizon assumption would not be correct. You would see a very large energy flux around the horizon. So, so it's actually a little bit strange because the black hole evaporates very slowly. So it's very hard to tell the difference between a permanent black hole and an evaporating black hole if the black hole is very large. You can always consider a large black hole sufficiently large so that its Hawking radiation is too weak for you to detect. However, if you decide to move towards the black hole, when you pass the horizon, you are going to experience complete different fate. So for the physically formed collapsing matter black hole, unruled vacuum gives you no drama at the horizon. But for permanent black holes, you would find actually a firewall around the horizon.
Excuse me. So in the case of Hartle-Hawking vacuums, you are saying still large energy momentum tensor near the at the near horizon region. Is it the point? In this, yeah.
Yeah, I actually that's what I remember, but
I see.
I'm not totally sure. If it's not true,
I suppose there's some computation of Hawking radiation for this Hartle-Hawking vacuum, and well, I do not remember correctly, but I suppose that this energy momentum tensor was regular. But
okay, yeah, then I should only talk about.
I'm not so sure. Yeah.
Yeah, sorry. Then I should only talk about the Boole vacuum. So this is the static permanent black hole. Then you would have a firewall. So this part I'm very sure. Yeah.
Yeah.
Thank you.
Thanks.
I'm sorry. So what
Yes.
is the argument to find a firewall for this Boole vacuum?
What is the argument? It's just a result of the computation. So using the same formula, actually, what happens is that you have two terms, right? So you have to tune these terms to cancel that term to get zero around the horizon. So once you change it, so for the unruled vacuum, this is Hawking radiation. This is some negative value around the horizon, they cancel. So now for the Boole vacuum, you turn this to zero, then you are only left with this term. So it's zero, yeah.
And it's diverging at the horizon?
It's finite in little u, meaning that it's extremely large for free-falling observers because little u is like c squared times t capital U, and c squared is extremely small.
So c actually enhances.
Yeah, that's right. So if this is of order 1 over a to the 4th, then for freely falling observers, it's 1 over a to the 4th times c to the minus 2.
Okay, thank you.
Basically, so this work, I think, gives people some more confidence about the assumption about the uneventful horizon or the unruled vacuum as the quantum state. So later on, Christensen and Folling, they had a paper to generalize those discussions to 4D. Although in 4D, we do not really have a complete knowledge about the vacuum energy momentum tensor. If you consider a conformal field, just as an example, you would have trace anomaly, you would have conservation law, as before in 2D, but then you have additional component in the energy momentum tensor. You have spherical symmetry, so you have only one additional component, but still that component is not determined easily. So you have to basically actually quantize the scalar field in a curved background. And this computation is very hard. So later on, there are a lot of works trying to compute that in the Schwarzschild background. And basically, there was no conflict between this picture. So the picture they proposed is just that everything in 4D works out as in 2D. So you have Unruh vacuum, Boole vacuum, and Hartle-Hawking vacuum. And then for the Unruh vacuum, you have for freely falling observers, you find an uneventful horizon, no drama at the horizon. So it looks like there are, some kind of nice things going behind so that these equations work out as equivalence principle suggests. So people, I think, often refer to this paper as the paper after which people sort of accepted the conventional model. I mean, actually, right after Hawking proposed information loss paradox, people have questioned this statement. So people like Boole would suggest that, well, you actually would get a large quantum effect. So you don't really know for sure what is happening around the horizon. So there's no paradox. But after this paper, I think, at least that's what people told me, that people start to accept the uneventful horizon. So this is one of the standard references for the conventional picture.
Can I ask a question?
Yes.
I mean, we have this Boole vacuum or Unruh vacuum as two choices, and so this choice of vacuum, one can view that as a choice of boundary condition at infinity, or how one can view, understand this choice of vacuum?
Right, so there are two ways to understand the choice. One way is to look at the boundary. So for different boundary conditions, you fix the function f and f bar, and that fixes the energy momentum tensor. Or you can think of it as a problem of initial state and time evolution. So for the Unruh vacuum, we have the initial state of a Minkowski vacuum in the infinite past, when the collapsing matter are still scattered around the whole universe. So the curvature is 0. And then in the thin shell case, the space inside the shell would remain Minkowski. So you have Minkowski vacuum inside the thin shell. And so that gives you the energy momentum tensor, also given that by the same formula, but inside the shell. Okay, so then you can determine F and F bar, and that would give you the Unruh vacuum. Or you can consider Boole vacuum, which is derived by assuming translation in time symmetry. So yeah, you have different ways of fixing the quantum state.
So in this where I mean evaporating black hole, in the situation of evaporating black hole, one would naturally have Unruh vacuum.
That's right.
That's what you're trying to say. Okay.
That's what I think almost everyone believes. That's right. Yeah.
Okay. Okay.
I'm actually, yeah, I mean, I'm going to say there's some loophole here. So right now I'm just presenting the standard story. You shouldn't ask me what I believe in right now. So anyway, now that you have the energy momentum tensor for the vacuum, then you can plug them into the semi-classical Einstein equation. So for example, TUU is of order, sorry, I'm missing square of order C squared times LP squared over A to the fourth, etc. And even just with the order of magnitude estimate, actually you can find a lot of properties about this geometry. So for example, you can deduce some features about the geometry behind the trapping horizon, but we have to first define the trapping horizon. So the trapping horizon is defined with the choice of foliation, and with spherical symmetry, the most natural choice is the areal radius. So you choose the areal radius equal to any given constant to define a foliation. And then you ask the following question. Usually when you are moving inward or outward, the areal radius should increase or decrease, right? If you are moving outward, it should increase. If you are moving inward towards the origin, it should decrease. However, the geometry may be non-trivial, so that in a certain region, either way you are moving, the areal radius is decreasing. So when that happens, we say you are in a trapped region. And the boundary of the trapped region would be where these two equation changes sign. So it would be where v derivative of r vanishes. Now, it doesn't matter which light cone v coordinate you use, because you are talking about this derivative vanishing. But you can ask about whether this is the outer trapping horizon or inner trapping horizon. If it's the outer trapping horizon, it means that after you move outside this region, when you move outward a little bit, you would have the normal situation. And that means you have the second derivative positive, etc. So basically, trapping horizon is defined this way. If you plot a Penrose diagram corresponding to the case with the trapping horizon, it would look like this. So on the left, I showed the Minkowski space. You have constant R curves like the green curves here. So when you move outward, this is say R equal to 1, the next one is R equal to 2, and then R equal to 3. So if you are moving out with a given U, when V increases, you will see that the value of R is monotonically increasing. But when you have a trapping horizon, what happens is that when you move out along a curve of constant U with increasing V, the value of R would increase and decrease and then increase again. So you would have points where derivative of R with respect to V vanishing around here and here. So that would be the outer trapping horizon and inner trapping horizon. So the picture would look like this. Now, if you plot the picture for a given instant of time of the geometry, it would look like this. So here you have a time slice of the 3D geometry plotted as a 2D surface. So you have spherically symmetric spheres as circles. If you are moving towards the center of the black hole, you see that the radius decreases, but then after you pass a point, it's increasing again, and then it's decreasing again. So this neck, where you have the smallest areal radius, is where you have the apparent, the trapping horizon. It's also called apparent horizon. And then, so the conventional model is like this. You have negative energy flowing into the horizon. So you have the energy of the matter here, and more negative vacuum energy flows into the horizon, so that from the viewpoint of an outside observer, the total energy behind the trapping horizon is smaller and smaller. The collapsing matter is still there, but you get more and more negative vacuum energy. As the total energy of the black hole gets smaller and smaller from the viewpoint of outside observer, the neck should look smaller and smaller. So in the end, if you have a complete evaporation, it's like the neck shrinks to zero. You get this picture people call the Wheeler's bag of gold picture. And then if it's detached, you say the information is lost. On the other hand, for many people, this is not really missing information. The information is still there. You are just unable to reach it if you happen to be outside. So some convention or traditional relativists, they do not think this is a big problem. I think I don't have time to show you that the trapping horizon is time-like, but it's in the slides. It's easy to see. You can use semi-classical Einstein equation to deduce that. And also, I don't have time to show you this, which is essentially giving you a contrast between two cases. The case with positive outgoing energy flux around the horizon or a negative ingoing energy flux around the horizon. At large distances, you assume you have Hawking radiation, so you would have an outgoing energy flux. But around the horizon, for the sake of energy conservation, you can have either case. The geometry for the two different cases is very different. That's, I'm going to skip, but if you like, you can read the slides. But I like to use a little bit time to review Hawking radiation in 3 minutes. But let me just give you the conclusion. The conclusion is that to compute Hawking radiation, you don't need event horizon. You can compute Hawking radiation in this geometry where everything is smooth. So basically what it's saying is just that the vacuum of the infinite past would move in through the center and then going outward. But the affine parameter for a massless wave is stretched when you compare the affine parameter of the infinite past and the affine parameter of the infinite future. Now, the affine parameter of the infinite past, dv, after passing through the center would turn into capital U. And we showed earlier that the relation between capital U and little u is given by this conformal factor. And if you do the calculation in below, which I will skip mostly, you will see that as long as the relation between capital U and little u is exponential function, then you will have a Hawking radiation with the usual spectrum people say you have for Hawking radiation. Now, this calculation is essentially done by assuming you have a free scalar field. But actually, you can introduce an interaction like this. You consider a free scalar field, massless field. Its equation of motion is like this. If you introduce interaction, you would have these extra terms. But when you go to the region close to the horizon, you will see that because the conformal factor C is very small, so the interaction term is actually almost completely irrelevant. So interaction of the field doesn't help you to bring out information because around the horizon, the interaction of the field with the collapsing matter is extremely weak. So this was checked by Lihi and Enru that this term has very little effect. And at the same time, the angular momentum also has very little effect. So basically, you don't really have to assume you are considering S wave. You can consider a multiple wave, but the angular momentum doesn't contribute, so you can actually take the iconal approximation and think of the light ray going along the radial direction. Now, the Hawking radiation rises because you have different time coordinates for different observers. And for your choice of the time coordinate, you would have corresponding creation annihilation operators. So I'm using C and C dagger for observers at large distances. And I'm using A and A dagger for observers in the near horizon region, where capital U and capital V are the appropriate coordinates for freely falling observers or for observers inside the thin shell. And then the Bogoliubov transformation relating little c, c dagger, and little a dagger tells you that if you take the vacuum for freely falling observers, namely the vacuum annihilated by little a, it is not a vacuum for the particle notion defined by little c. So the particle number operator for C, the particle number operator for distant observers, for this freely falling observer's vacuum would be non-zero, and that gives you the spectrum of Hawking radiation. So all these calculations can be done without the assumption of event horizon. All you need is this exponential relation between the coordinate you used to define vacuum and the coordinate you use to define observation. Now we showed that their relation is given by C, but the Schwarzschild metric gives you C equal to 1 over, C equal to 1 minus A over R, which can be written as an exponential form. So you do have this exponential relation between capital U and little u. So that's why you have Hawking radiation. If you modify the Schwarzschild metric such that C still has approximate exponential form, you would still get Hawking radiation. Let me skip that page, which only refers to the Unruh effect as another way to interpret Hawking radiation. So I like to emphasize a point. We talked both about vacuum energy momentum tensor and Hawking radiation. These two are actually different, although closely related concepts. Hawking radiation has to do with how you define particles. And vacuum energy momentum tensor does not necessarily have anything to do with particles. You can have vacuum energy momentum tensor without particles. But Hawking radiation also contributes to the vacuum energy momentum tensor. So for example, at large distances, for the Unruh vacuum, at large distances, you have no ingoing energy flux. You have outgoing energy flux, which is just the same as Hawking radiation. Around the horizon, the vacuum energy momentum tensor outgoing part is 0, the ingoing part is negative, and also you have no Hawking radiation around the horizon. But for fiducial observers, you would have particles around the horizon as well. So actually, strictly speaking, for an eventful horizon, you need not only that the vacuum energy momentum tensor to be small for freely falling observers around the horizon. You also need no particles, the absence of high energy particles around the horizon. So you have to impose both conditions to ensure that you have an uneventful horizon. Okay, so that's about what I want to say, review for the conventional model. And now the question is whether what I said missed something. Was there something dubious, or was there some additional checks we should have done, but we have not done yet? So if everything works out, if there's nothing new we can check, if it's really a very solid model, a rigorous model, then we would have to give up the decoupling principle, perhaps. So this is the end of my second talk. Thank you.
Thank you very much. Okay, so do you have any question to the lecturer, Pei-Ming?
I got a question.
Please.
or I have a little confusion about your definition of U and V coordinate. So in the slide where you can you explain this word, I mean Hawking radiation. That's going too much. There, or with figures.
Sorry, keep going or what?
Well, I mean, in the figure, it looks like, well, I mean, your here. The coordinate U and V seems interchanged. It looks like U is ingoing and V looks like outgoing there in that figure.
Yes, yes. So if you have an outgoing wave, the wave, I mean, the wave
is ingoing coordinate.
U is
So
the retarded.
It seems to me, I mean, you explain in such a way that TUU is the outgoing Hawking radiation, but it seems to me, I mean, in this figure, somehow U is ingoing.
Yeah, well, those have to do with your convention, I guess. I mean, if you put the indices upstairs, then TUU, lower stairs UU would actually be TVV upstairs. So, I mean, that has to do with your convention. But I think this is correct. So we define U to be the retarded light cone coordinate. So U is T minus R, V is T plus R. So if you have a wave like function of T minus R, then that is an outgoing wave, right? So as time increases, R increases, the shape remains the same. So a function of T minus R or a function of U is an outgoing wave. Now a function of U would contribute to TUU with U in the lower, at the lower place, because you take U derivative of the function F. Is that okay?
I can check right now. Yeah, it's confusing to me.
Yeah, well, I could make a mistake, but I mean, then you just interchange U and V.
Yeah. Well, okay.
So, can I ask a question as well?
Please.
Yes, please.
So, the point is that, like, in order to calculate this, the expectation value of the stress tensor, right? I mean, the quantum stress tensor. In principle, I don't need to assume that. I mean, I have some kind of a free scalar field, right? So it could be, for example, any 2D CFT.
That's right.
But then this free field picture is necessary in order to derive this kind of annihilation and creation operators to derive the Hawking radiation. Is that correct?
Right.
So you could still go through, like, I mean, with some kind of generic strongly coupled CFT, but in order to see the Hawking radiation, you would still need to have some kind of free field picture, some perturbative picture at least.
That's right, because yeah, Hawking radiation is about these particles. So
right.
Yeah, you need that picture.
Right.
Right.
And then, please go ahead. Okay, so a related question was about this four-dimensional picture. So generically, right? I mean, so there would be some part that corresponds to like maybe the Casimir energy. So I guess that would be related to in 2 dimensions to this part that involves like the C, right? So the part that comes from the conformal anomaly in 2 dimensions.
Sorry. Yeah, you would have a trace anomaly, and sorry,
Right.
what did you say?
So that would contribute like to the Casimir energy, right? And then probably like, I mean, we cannot determine like, I mean, the full stress tensor, I mean, because it has like more components in higher dimensions.
That's right.
But for example, I mean, if I look like in supersymmetric theories, like, I mean, if I impose some kind of extra symmetries, like, I mean, let's say not supersymmetric black holes, but just the theory I'm quantizing, like, I mean, if it's supersymmetric, then there can be more restrictions, right? And then
that's right. Yeah. So actually, people have done a lot more than what I said here. These are the earlier works. After these,
right.
People have considered various different 2D, 4D models. Basically, they all got pretty much consistent picture. Although I'm suspicious that if they don't get a consistent picture, they wouldn't publish it. So, but
Right.
almost all the results are consistent. Yeah.
Right. Okay, thank you.
You're welcome.
Related to the question is that, I thought that this 4D to 2D dimensional reduction. So if the area of the black hole horizon is large enough, then we can discard all of those Coulter-Klein kind of excitations. So 2D computation should be believed to be valid. Is that the understanding?
You mean you don't have to use the argument for small c?
No, I mean, so 4D is difficult because you have more components, but in principle, 2D approximation should be good when the area is big enough. Is that correct?
People don't seem to all agree on that because for a large, you are saying for a larger black hole, the approximation is better. But for larger black hole, you have more lower energy angular fluctuations, right? So I think people say that if you integrate over all these angular fluctuation degrees of freedom, actually you could get something quite different. Although in the end, people had actually used numerical simulations and analysis to show that the result is actually not too qualitatively different. Yeah.
No, I see. So 2D is actually not an approximation in any sense.
Is there a priori not necessarily a good approximation? In the end, it turns out to be okay.
No, I see. Yes. I have one more question. So before you got to this Hawking radiation part, you considered this trapping horizon. I think I missed the importance of that part. So, so you have two cases. One is outgoing positive energy, and the other is ingoing negative energy. And depending on the choice of those, you say that the space-time picture would be very different. Is that the point?
Right. So I skipped that part, but this is a crucial difference. So the conventional model picked this choice, a negative ingoing case. The KMY model, for example, picked this choice. The geometry is totally different. For example, you can use the outgoing Vidia metric as an example for TUU positive. So you write down the usual Schwarzschild solution in terms of the coordinates U and R, and you allow the Schwarzschild radius to depend on U, and assuming that A decreases with U, then you have a corresponding outgoing energy flux. Then you can see that the trajectory of the trapping horizon is space-like, and it's shrinking. So it means that there is no causal matter that can catch up with the shrinking trajectory of the trapping horizon, so that the trapping horizon would never emerge. It would always be hidden under the matter. It would actually never appear. So you need the ingoing Vidia metric in terms of V and R, allowing A to change with decreasing, so you have a negative TVV. Then the trapping horizon is time-like, and then it's easy for collapsing matter to enter the trapping horizon for the trapping horizon to emerge.
So these two choices correspond to what you described as for the Unruh vacuum.
Yeah, so the Unruh vacuum picked this one.
Yeah.
Yeah, so this one would be contradictory to the statement that freely falling observers should see nothing happening. For freely falling observers, this is a large energy flux outgoing.
Okay. So your picture of this bottleneck type geometry is for this negative ingoing flux.
That's right. That's right.
So if I follow this argument, then does it mean that information loss is not a problem since there is a baby universe and information should be stored there?
So that's what some people think, but I mean, for holographic principle, you don't really like this, right? Because the entropy inside could then be arbitrarily large, but you have a tiny horizon area.
I see.
Yeah, so, but that's why people like Andrew thinks this is no big deal. I mean, this is nothing special. You don't have to worry about information loss because it's just not accessible. It's not lost.
I see. So you are going to show that there could be a loophole in this, this scenario may not happen. Okay, thank you. So is there some other question?
Ask you one question.
Please.
So let's go to your Bogoliubov transformation. Right. So here, this transformation, I mean, just is just between what I mean the free falling and the so. You see, if we have particles in free falling, and if we go to non-free falling, well, I mean, who is staying out there? I mean, it involves some singular coordinate transformation, right?
Not necessarily, because you could be talking about a finite region. So I mean, all these phenomena are local physics, right? I mean, you don't have to really go to the end of the universe to detect Hawking radiation. You just need a finite space large enough. So we are talking about a finite region in space in the early stage of the evaporation where everything's smooth.
Right. So you emphasized that one before, but I was still thinking just a near horizon, what is happening. So
yeah, so it's like a Unruh effect, right? So in Unruh effect, you have Minkowski vacuum, but if you are accelerating, you would detect particles. Now, you don't have to accelerate for infinite time, right? You just accelerate for a while, you would see particle triggering your Geiger counter. So here also, you only need a finite region. And of course, with a finite region, you probably should use a basis which is a suitable basis for this finite region. And so people have actually tried to do that. So in that case, you should not really use this Fourier transform. You should use a more suitable basis if you specify this finite region. But then approximately the result would still be the same.
my question is very naive one. Don't take it very seriously.
Oh.
What I'm thinking is that if we really consider this Hawking radiation not during this infalling time of a black hole formation, but I mean consider large black hole which is already formed, and then if there is a air formation, then very naively, it should begin just near the horizon and where there is a coordinated singularity. And if we have a particle spectrum in one coordinated system where there is no singularity, then what I want to ask is that if we go to, our usual, outside coordinator, then there must be some, it is not really clear whether the resulting spectrum is a still particle spectrum. So that is what I wanted to ask. So I feel a little bit uneasy about this value of transformation. Because it is, mapping from the particle to particle.
Right.
Right. So that is my question.
So you're asking whether such a Bogoliubov transformation is, so mathematically you have no problem, right? You are asking physically whether, in what sense it's really a particle for which observer?
Well, the complete set, right? Actually, this is a mathematical question.
It's a mathematical. Yeah, so for the mathematical question, I think this is
we have a system of a particle, suppose, in one coordinated system where we don't have any singularity. And then when we transform this spectrum to a coordinated system where there is a coordinated singularity, so is it true that there is a, the usual, Fourier transform works or not?
Right, so then it's not really the Fourier transform. So in that case, as I said, you should use a proper basis, not these exponential functions. That's right. So you should suitably define your basis of functions, and your notion of particle would have to be changed slightly. So your particle would not be a particle of given energy, right? To assume that a particle has a precise energy, you are actually already assuming a region of infinite time. So if you are in a finite region, actually you have to modify your notion of particle. Yeah, but I think people have done similar things before. So that, and also the coordinate in the end is also smooth. So we have a finite region in space-time and two sets of smooth coordinates. You can try to define the basis of functions better, corresponding to a slightly different definition of particle. How to define, how to detect them is another question, but yeah, mathematically, it works out.
I'm sure that many people worked on it, and then maybe great care has been done. I'm very sure, but I still don't understand whether this coordinated singularity really doesn't introduce any problem.
Sorry, where is the singularity?
I mean the in usual, black hole. The Shibarachi shield. We do have GTT is 0 at the horizon, while in free falling system we don't have such a problem. So
right, but,
very near the the horizon, where I suspect that the evaporation mechanism is working mostly there. It is not very clear to me that if you have a particle in free falling system and you still have the particle-like spectrum in the near horizon infinite observer coordinate.
Actually, I'm considering the region, without the event horizon. So this is the finite region. So there's no singularity.
Avoiding some maybe essential problem source. I'm not sure.
Okay.
Whether we can really avoid the handling this near horizon region. You don't have any problem because you didn't consider near horizon, right?
This is near horizon.
But near horizon, but you are avoiding the singular region, so.
Right. This is the near trapping horizon, not the near event horizon. So event horizon happens over there, but you would already have Hawking radiation well before that, right? So you have a black hole, it's huge. So it's going to take 10 to the 10 years to evaporate. Now it's evaporated, say, 1/2 of its mass already. You see Hawking radiation outside, but you are still roughly 10 to the 10 years away from the final point of complete evaporation where the event horizon is. So the event horizon is very, very far away from the place where you can already detect Hawking radiation. So I'm talking about the Hawking radiation detected at that moment.
But anyway, I am non-expert, so I wouldn't argue anything to opposite to what so-called conventional people's thinking. But so do you think that this coordinated singularity doesn't create any problem?
Yeah, for me, because there is no singularity in the neighborhood I consider, so it doesn't create a problem for me. For some other works, people also use conventional model to talk about the event horizon and so on. For those works, I wouldn't know. Yeah, so I try to avoid all the singularities to avoid such problems.
I mean, so what I'm complaining is that by avoiding this coordinated singularity, probably it looks like that maybe people are avoiding the some essence of the problem.
Oh,
I don't know.
I see. So I see. Okay.
Right.
Okay, thank you very much. Since time is approaching to the next session, so maybe we cut up the question session right now, and let's take a break. So thank you, Pei-Ming, for the second part, and we will resume the session at 3:30. So please take a rest. Thank you.
Thank you.
So everyone is not showing the video. So Pei-Ming, from you, it's like you are talking to just the list of names, but yeah, I'm sure everyone's listening.
Yeah, but there were questions, so I'm sure someone's.
Yeah. So suddenly the question comes in.
Right.
This is usually the case for Zoom seminars, lectures.
Right. Yeah. I thought about just taping, a part of my video and then use that as a background. So even when I'm not around, people see my face.
Sure. Then the university will, fire us. They collect the video. Okay, so it's about time. Pei-Ming, are you ready?
Yes.
Yes, thank you. So let's enjoy the third part of Pei-Ming's lecture. It's on the road for finding the loophole of the conventional models. So we are looking forward. So Pei-Ming, would you please start? Thank you.
Okay, thank you. So yes, I hope to claim that I have found the loophole in the conventional model. So let's review the assumptions of the conventional model. So the key point is to find something that makes these uneventful horizon or the Schwarzschild approximation invalid. So we want to say that with the same framework, theoretical framework of semi-classical Einstein equation and low energy effective field theory, even if you start with an eventful horizon, maybe after a while, the unruled vacuum would evolve to a different quantum state, because what we saw earlier was that if I assume Schwarzschild approximation and if I assume unruled vacuum, then you seem to get a consistent picture, but it doesn't tell you that over time evolution, they would stay in the same state. So this is one thing that you can try to explore. In order of doing that, one thing we have to do is to first find a better approximation of the near horizon geometry, because earlier we have this Schwarzschild approximation showing that it's consistent. But if we are questioning the validity of that, we hope to do something better. So what we do is that this is through a series of works I did with Yoshinori Matsuo-san and Yuki Yokokura-san. We studied the near horizon geometry, assuming the energy condition of the uneventful horizon, but without assuming that Schwarzschild approximation is good everywhere in the near horizon region. We only assume that Schwarzschild approximation is good outside the near horizon region. Use that as a boundary condition to solve semi-classical Einstein equation. So that's one thing we do. In principle, if we know what is the collapsing matter, we can also find the geometry inside the matter. But as we mentioned earlier, we want to consider all possible types of matter. So we try to skip that part. We just study the near horizon region outside the surface of the collapsing matter. Another thing we will try is to look at other interactions in the low energy effective theory. Earlier, we mentioned that if you consider ordinary interactions, renormalizable interactions, such as phi to a certain power for the scalar field phi, actually those interactions are not going to give you strong interactions to bring out information. So we should consider non-renormalizable interactions as well. So these are the two things we will do, and then we will check whether there will be high energy events. So for the sake of understanding near horizon geometry, we still assume spherical symmetry. So the onsets of the metric is like this. We use semi-classical Einstein equation, and what we know is that the right-hand side, this vacuum energy momentum tensor is assumed to satisfy this condition, the condition following equivalence principle, and is also verified in various 2D, 4D models. But we will not assume that the Schwarzschild solution is a good approximation inside the near horizon region, but only well outside the neighborhood where the quantum correction could play an important role. So here I choose a parameter n, supposed to be large number. So I assume that when r minus a is much larger than a over n, the Schwarzschild approximation is a good approximation. And then skipping the details, you can look at our papers if you wish to know the details, but you can find a linear combination of the semi-classical Einstein equation to solve the conformal factor to this form, where we have a certainty in powers of C. But as we know, C is going to be smaller and smaller as you move deeper and deeper into the near horizon region. So you can think of that as something you can do expansion with. So we will consider expanding quantities in powers of C. So C will go to tiny number, it could be much smaller than Planck length over Schwarzschild radius. It can be arbitrarily small for an arbitrarily large black hole. So it's a good approximation to expand quantities in powers of C. And here, this expression is actually very similar to the Schwarzschild expression for C in the near horizon region. I showed that expression a little bit earlier, but it's essentially the case when you have this function A and A bar both given by the same constant. In that case, you would retrieve the expression of C in the near horizon region for the Schwarzschild solution. So what we gain by solving this semi-classical Einstein equation is just that we find that you still have this factorized form of C into a function of U and a function of V up to a factor of R. And this A and A bar, they are relatively functions of V or U only. They could be thought of as the Schwarzschild radius at the boundary of the near horizon region, where you take a fixed tiny slice of U or V, and then you get a Schwarzschild radius over that slice. But since you're taking the slice in different directions, in principle, they do not have to agree. On the other hand, they cannot be too different as well, because just outside the Schwarzschild, just outside near horizon region, the Schwarzschild approximation should be good. And we know that as an order of magnitude estimate, dA over du is proportional to the Planck length over Schwarzschild radius squared. A and A bar are supposed to be of the same order of magnitude. They're supposed to be very close. So we're studying this near horizon region with the boundary given by r minus a equal to a over n, and also the surface of the collapsing matter. And in this gray area, this is a good approximation of the conformal factor as an expansion of the 0th order expression of C. With this expression, you can now go on and solve semi-classical Einstein equation with both C and R expanded in powers of the 0th order solution of C, like that. And then it's straightforward to find higher order solutions. For the calculation below, we only need the 0th order approximation for C and the 0 and 1st order approximation for R. So byproduct we found with this result is that due to this exponential feature of C, actually the proper distance between the trapping horizon and the surface of the collapsing matter is actually always very small as long as you are still in the early stage of the evaporation. So let's say that your black hole is evaporated to 1/nth of its initial mass, then the proper distance between any 2 points in the near horizon region is bounded from above by Planck length times n to the 3/2. So say at the page time when n is equal to 2, basically any 2 points in this near horizon region is essentially around the Planck length or smaller. So actually that gives you a warning saying that although you can see a large change in V, actually you may be talking about a tiny space in the near horizon region. And your low energy effective theory actually is maybe not so reliable. But we want to do, yes.
So, sorry, what is the input of this analysis? So what is the assumption?
The assumption is that we have essentially the assumption of Schwarzschild approximation outside the near horizon region. We use that as a boundary condition for the near horizon region. And we use semi-classical Einstein equation. And also we use the energy condition for the n-eventful horizon. So it's here. So
here, so this T menu are given or just assumed?
It's assumed to be given by this order of magnitude. That's right. Yeah. So this is what we confirmed.
So what you did was, so assuming this energy momentum tensor and solve this Einstein equation, you got this answer. Is this correct?
That's right. That's right.
Thanks. Thank you very much.
You're welcome. Okay. So that may be a little bit too much to remember, but essentially to understand qualitatively what I'm going to say, it's enough to remember this approximation, the lowest order approximation. So earlier I had the conformal factor expressed as an integral of u and the integral of v in superposition, but over a sufficiently short period of time, the Schwarzschild radius doesn't change too much. So this is still a good approximation, which is the same approximation as Schwarzschild solution. On the other hand, the areal radius you have to keep its V dependence because that is the effect of the back reaction of the vacuum managing momentum tensor. Remember that in the conventional model, you have negative energy flux flowing into the horizon. So that results in a time dependence of this value, A bar, which is the lowest order approximation of the areal radius in the near horizon region. Okay.
Excuse me. So I missed why this U dependence disappear in this?
V dependence?
U dependence. So your RUB does depend on V only. Is this so? Why?
Oh, so it depends on U. So for the Schwarzschild solution, the leading order approximation is just the Schwarzschild radius. It would be a constant. So for Schwarzschild solution, the near horizon region has almost a constant areal radius. The next order solution would have explicit time U and V dependence. Now, including the back reaction of the vacuum managing momentum tensor, the leading order term already acquires a V dependence.
So why only V dependence? So maybe I missed that.
Oh, no problem. So I didn't show you all the details, but the intuitive idea is that around the near horizon region, TUU is almost 0.
Oh, that is the reason.
Dominates.
But not so.
Yeah. So TVV gives you a negative energy inflow, which changes the Schwarzschild radius.
Okay.
Yeah, but TVV accumulates over change in V. So it is this A bar V that's changed by TVV. So this is reflected in the areal radius of the near horizon region.
I see.
But anyway, this is the solution to the semi-classical Einstein equation.
Thanks.
Yeah. So one thing to keep in mind is that when you go deeper into the near horizon region, the value of U increases and the value of V decreases, so that this exponent is giving you a larger negative value, so that the conformal factor decreases exponentially. So as you move in the direction of the arrow, C quickly goes to a tiny number. So when the numerator, U minus V, changes by an amount of A times log A over Planck length, this exponential factor is changed by Planck length over A to some power. So you easily get a high power of Planck length over A from this exponential factor when U and V is changed only a little bit. So that was the near horizon geometry. It's actually in the end not too much different from the Schwarzschild approximation. So now let us look at the other thing we want to explore, which is turning on non-renormalizable interactions. So we mentioned in our last talk that people have considered interaction terms. So, but however, around the near horizon region, those interaction terms have very little contribution. So you can ignore them. So in order to introduce some interaction to change the free field evolution, not in order to, but to check whether it happens, we have to consider non-renormalizable interactions to be complete. So in general, when you have a low energy effective field theory, in principle, you not only have the free field part and renormalizable interaction, but also you have these curvature tensor and also higher derivatives of the scalar fields. All these terms should appear in the effective field theory. Although the non-renormalizable terms, they are weighed by factors of 1 over Planck mass or positive powers of Planck length. So their contribution are typically very small, negligible when you have sub-Planckian or sub-cutoff energy scale events. So actually people have been considering the possibility that the effective theory is not dominated by the free field part, but people have mostly checked just the curvature invariance. And all the curvature invariance remains small, including the back reaction of the vacuum energy momentum tensor. One simple way of arguing for this, although of course we have checked this explicitly, but to see that the result is small, you can argue that since the leading order correction to the areal radius is a V dependence, on the other hand, V dependence is something that has no invariant meaning because you can do a Lorentz boost to change the V dependence to arbitrarily fast or slow. So such V dependence cannot give you a large curvature invariant. So if you check explicitly, even including the higher order terms in the C expansion, all these curvature invariants are still small. They are still giving you the characteristic length scale of the Schwarzschild radius. So people have checked these. Actually, they also checked that on a nice time slice, the external curvature is also small. So if you look at the geometry is still very smooth. So we're supposed to, sorry, this is what I already said, you can do a Lorentz boost. So you do not expect a large curvature. So we want to consider the non-renormalizable terms, in particular, the higher derivative terms in the effective theory. Now, Tuft had pointed out the problem of transplanckian modes involved in the derivation of Hawking radiation. So because of this definition of frequency for a particle or quantum fluctuation for distant observer and free-falling observer is very different. They differ by this du over du factor, which is proportional to the conformal factor. So when C goes to 0, a small frequency for distant observer can be a transplanckian frequency for freely falling observer. Now this high frequency or transplanckian frequency mode should not be taken directly as a reason to abandon the effective field theory, because this is not an invariant quantity. You can always do a local Lorentz boost, either in little u or capital U, so that the frequency, both omega u or omega capital U, are arbitrarily large or small. So just like we can still use standard model to predict scattering amplitudes for these ultra high energy particles in cosmic rays with particles on Earth, we should not immediately abandon these transplanckian modes, because that's the result of a particular choice of the coordinate. So what you need is actually a quantity, an invariant quantity to be transplanckian. Then you would actually can say that effective theory can be in trouble. So if you have two particles, one outgoing, one ingoing of frequency omega u and omega v prime, then you want this quantity on the left-hand side to be much smaller than the Planck mass squared to justify the use of effective field theory. But more generally, if you have a background characteristic function f, which has some v dependence, then you also need this combination to satisfy the same constraint, because if you think of what omega prime v is, it is such a quantity. So whenever you have characteristic length or energy scales, composing an invariant quantity which goes beyond the Planck scale, then you are in trouble. Otherwise, you are fine. You can also generalize it by taking higher derivatives, or consider two different functions, f and f bar, and both raised to higher derivatives. And you need all of these invariant quantities to be cis-Planckian in order to claim the validity of effective field theory. In the following, we will especially pay attention to this particular combination. So we can consider a background field as the function f here, and check whether for the Hawking radiation of frequency omega u would give you such an invariant quantity that is too large. So the Hawking radiation has a spectrum that's peaked at omega u of the order of 1 over a. And then we have this areal radius, or the Schwarzschild radius a bar, as a function of u, giving you the background geometry. So we can use that as the function f, and then compose an invariant quantity. So this quantity is invariant under local Lorentz boost. Now this derivative is given by this order of magnitude estimate that's telling you how large Hawking radiation is, so that how fast Schwarzschild radius changes. And then if this quantity is much larger than the Planck scale, then your effective field theory is no more reliable. So for this condition to hold, what you need is that this conformal factor is much smaller than this tiny number. But as we said earlier, this conformal factor is an exponential. It's easy for it to be arbitrarily small. You only need this numerator in the exponent, u minus v, to be larger than a times log a over Planck length in order to get this condition satisfied. So if you go deep enough into the near horizon region, you can satisfy this condition, and then you have an invariant quantity that says that your effective field theory is in trouble. Is there any question?
So sorry. I'm sorry. It seems that what you're saying is the coordinate singularity seems to be important.
There's no singularity here.
Because what you are doing is, what you are saying is, if you are going deep into the, near horizon region, right?
Right.
So what is the source of the trouble there? The only thing I can imagine is that you do have a coordinate singularity there.
I don't have coordinate singularity because C is bounded from below by a finite number. It's just that that number is extremely small. But so, as long as it's not zero, it's not a singularity.
What I'm saying is that, the proximity effect. That is the only thing that makes that thing big is just a G mu nu, right? Inverse G mu nu. That makes the thing big there, right?
That's right.
So it is the coordinate singularity which makes the trouble.
There's no singularity because C is not zero.
Oh, no, I'm saying it's big there. I'm not saying it's a singular. Even
okay.
Just avoid the singularity itself, as far as you are close there, it blows up.
Yes, yes. So it's not a real singularity. It's just that this number is very small. But I will also talk about the viewpoint of another coordinate system, capital U and capital V. So there, for capital U and capital V, the value of GUV is always 1.
Okay, anyway, I'm very happy that the people are considering such effect. Okay.
Okay, thank you.
May I have a question?
Yes.
So my concern was that previously you said that the region of this gray part in your Penrose diagram is very small.
Yes.
And but for this condition to actually happen, then don't you need to take U minus V to be large?
Yeah, U minus V is actually could be very large, but the proper distance is small because C is an exponential function with a small coefficient.
I see. So this condition is still within the region of validity for this.
That's right.
I see. How do I see it?
So you see that because of this exponential function, when you compute the proper distance, you are doing an integral, right? Now, the integral of an exponentially decay function actually is independent of how far deep you go, right? Because the deeper part has no contribution to the integral. So when you compute the distance, actually only the first part of the integral contributes. So that's the reason, but you can actually go arbitrarily deep into the near horizon region without actually changing the proper distance much.
I see. I see. So the violation of this inequality can be arbitrarily bad?
That's right. It can be arbitrarily bad. That's the point.
Nice. Thank you.
Welcome. So for Schwarzschild metric, you don't have back reaction, so you don't have this invariant quantity. You could have other invariant quantities, but when you have translation symmetry, you expect conservation of energy and so on. So you may not get a problem there. I'll talk more about that. So right now, I'm just saying that superficially, you have some invariant quantity that could be very large to invalidate your effective field theory. And also, I pointed out that the right-hand side is actually just the definition of scrambling time. So it says that over the order of magnitude of scrambling time, this value of the conformal factor would be small enough to give you a Transplanckian invariant quantity. Okay, so of course you can consider more general invariants, combining the scalar field and also curvature tensor components. But again, in principle, you get these inverse factors of the metric. In particular, if you consider the UV component, you get these 1/c factors. So when C is very small, you get very large factors here. And U derivatives on the field would give you factors of the frequency omega U. And then the V derivative of the geometric quantities would typically give you V derivatives of this function A bar. So you can think of many possible combinations that would all give you similar invariant quantities that would give you Transplanckian invariant quantities within scrambling time. I mean, you may get a different coefficient here, but with a finite coefficient, you can compensate an arbitrary large power of LP over A. So if you get LP over A to the 10th power, in order for a certain combination to be large, you are only changing this factor of 2 to 5. It's still scrambling time order of magnitude.
So Pei-Ming, why do you call this scrambling time?
I'm just following the definition of Susskind et al. About, when they talked about complementarity, they also talked about the scrambling time, which is the time information of collapsing matter that's scrambled and then come out of as Hawking radiation.
Right, but here I would have thought that so if I want to violate this inequality, then I need to go to the region very close to the horizon.
Right.
So not the time scale, but some spatial distance scale.
Right,
so,
right. Yeah, I'm always thinking from the viewpoint of outside observers. So U is, I think of U as my time coordinate. So if I think of the collapsing matter falling around the speed of light, it's falling at almost constant value of V. So if initially the surface of the collapsing matter is not deep enough, you wait a little bit, it gets deep enough. And the time you need to wait is the scrambling time.
I see.
Yeah, so, because this expression is cut off by the surface of the collapsing matter.
I understand that interpretation, but can't we think about this as some distance scale away from the horizon?
Yes, it's actually, that's right, more like a space-like separation that matters. So I'm just saying that the space-like separation increases over time from the moment when the trapping horizon emerges.
So if I replace all the argument for the eternal black hole, then this distance scale distance scale is improper distance. What is the expression for this distance from?
It's actually the same because the this conformal factor has the same expression for Schwarzschild solution.
Mm-hmm.
So I'll explain later why, you know, for Schwarzschild solution, actually there is nothing to worry about. So here, this is more like a very hand-waving argument saying that when you see large invariant quantities to be large, you should get worried, but it doesn't really imply anything wrong.
Okay. Okay. Thank you.
So to see that, so I was saying that in all these combinations, in all these invariant operators, you typically get large factors of 1/c when you have higher derivatives. And so that as c becomes very small, you get easily large invariant quantities. But as we said in the first lecture, to actually have a resolution, what you need is more precisely to show that when you have, I mean, if you don't want to break the coupling principle, then what you need is to say that Hawking radiation plus effective field theory would lead to high energy events. So we want to check whether those large invariant quantities would actually lead to the creation of high energy events. So that would mean you have to do some concrete computation. And for the Schwarzschild solution, for the static solution, you will not get the creation of high energy events, but with the dynamical solution, you will. So the concrete calculation we will do is the following. We calculate the transition amplitude from the en-route vacuum to excited state with particles. So the effective field theory does not have to include all states, but there are 3 types of states that must be included if you want to say you are actually working with an effective field theory for this problem of black hole evaporation. So firstly, you have the en-route vacuum because that's the assumption for the initial state. And also you can have particles of arbitrarily low energy, right? You cannot just have the vacuum only without any other states. And then another state, this is more unusual, but you need it because when you claim that you have a Hawking radiation, you are claiming that you have particles with approximately this spectrum given by the expectation value of the number operator for the number defined for distant observers. So we call it C. So this quantity, which represents the spectrum of Hawking radiation, is also the norm of this state, C acting on the en-route vacuum. Now using the Bogoliubov transformation, this annihilation operator is a superposition of A and A dagger. So the creation operator survives after acting on the en-route vacuum. So this state is actually just a superposition of 1 particle states for freely falling observers. So the effective field theory must include the following 3 states in order for you to say that you do have Hawking radiation. Okay, so now we consider the transition from the en-route vacuum to a final state including particles such as C acting on vacuum and other very low energy particle states. And then we consider operators, invariant operators as interactions that could lead to such a transition. And so we just calculate this transition amplitude as the, in this way. So in the middle, you have the invariant operator, and then you have the initial state, the en-route vacuum and the final state, which includes this state that has to be well defined. And then you have these powers of Planck mass to suppress this amplitude. So typically people do not consider these contributions because you are suppressed by the high power of the Planck mass. On the other hand, we saw that these inverse metric factors gives you inverse factors of the conformal factor. You get this C minus N factor. So actually, you can easily get a huge factor around here. In the other places, like the coefficient or other places, you can get a large suppression by factors of Planck length over Schwarzschild radius. But as long as that power is a finite power, you can always easily compensate it by going to a deeper region in the near horizon region over the scrambling scale. So these factors, exponential factors, tells you that you can get large transition amplitudes. Now this is just a roughly hand-waving statement. Whenever you have conservation loss, you just happen to get 0, right? So when you have time translation symmetry, like the static Schwarzschild solution, you have a conservation law, which would remove any transition that violates conservation of energy. So you don't get this amplitude for a static Schwarzschild solution. But if you have a dynamical background, then in general, you will get such a factor. Now there will be some suppressions. So in actual calculations, maybe you still get 0 contribution when you only keep the leading order approximation. You may go to next order approximation, so you get extra positive powers of C, but you can just raise the number of derivatives to compensate it by more factors of C inverse. So generically, what's happening is that when you try to compute a transition amplitude or something that is physical, it's a Lorentz invariant, it's typically an integral over space-time, you get a certain power of Planck length over Schwarzschild radius coming from the coefficients or from derivatives of the fields or from the curvature components. But with derivatives, you always need GUV to compensate, to make invariant combination. So you always get some powers of C inverse. And the more derivatives you have, the more factors of C inverse you get. You will also get more factors of LP over A when you have more derivatives, but those are easily compensated. So this tells you that you would get particles popping out of the vacuum due to higher derivative interactions within scrambling time. So starting to count when the collapsing matter enters the near horizon region so that Hawking radiation starts to appear, you would have to have this C acting on vacuum states to be well defined in your effective field theory. And then you would have to have this invariant quantity, this transition amplitude going larger and larger. And before scrambling time, it's too large to say that effective field theory is still valid. Is there any question?
Can I ask a question?
Yes.
Here you mentioned the scrambling time. So does it equal to summarization time, or how to translate scrambling into Chinese or Japanese?
Scrambling, can someone help me? I'm poor in both Chinese and Japanese. That's a terminology other people invented. So I'm just calling that number scrambling time. 搅拌, scramble, like scramble eggs. You are mixing something up. So people invented this term when they considered how information of collapsing matter should be distributed in the Hilbert space and then come out as Hawking radiation. Yeah, but here it doesn't really, yeah, maybe I shouldn't use this term in this scenario because in this description, we don't really talk about that at all. So it's just a coincidence.
Okay, thank you.
May I have a,
yeah, please.
Sorry, thank you. As far as I understand, irrelevant interactions in a steady state or equilibrium state can become relevant or more precisely important in non-equilibrium or with dynamical process. Do you have any other example for in other processes, in generally speaking? Usually, yeah, higher data.
Yeah. Sorry, you mean not black holes or still?
Yeah, I mean, yeah, generally. So irrelevant higher order gradient interactions usually irrelevant, but some in equilibrium. But as far as I understand, what you are saying is even such processes can become relevant. I mean, important in non-equilibrium or dynamical. I mean, I think this is maybe somewhat general. I don't know.
Yeah.
Do you have any physical example or?
No. So actually, maybe I should be more careful. So firstly, we assumed that you have this state, right? Because if you don't have this state in the effective field theory, then you don't know what is Hawking radiation. Maybe you don't have Hawking radiation at all. So assuming you have Hawking radiation, you would have, you would have to have such large transition amplitudes. So that's what I'm saying. And also, I should also emphasize that the value of C doesn't suddenly just become tiny, right? So C initially is not too small before black hole forms. And as the matter collapses deeper and deeper, the value of C gradually increase. So actually, well before the scrambling time, you would already have some tiny amplitude, tiny probability of seeing particles coming out of vacuum. So at that time, when the invariant quantity is still not as large as Planck scale, still smaller than the Planck scale, you would see a small probability. You would see sporadic creation of particles, but you would start to see something first. And then before this invariant quantity becomes really Planckian or trans-Planckian, the theory should not be valid anymore. And then what really happens would depend on your UV theory. Yeah, but there are other examples, similar examples, such as the early universe, right? So for the early universe, you also have this inflation, which if you trace backward in time, finite size fluctuation at the early time of inflation could be of an arbitrarily short wavelength. And then people have also talked about trans-Planckian problem. Yeah, so there are other cases which could be related. But then again, so it depends on some of the details. So like here, generically, you get a large quantity, but if you have energy conservation due to translation in T invariance, then this quantity would necessarily vanish anyway. You don't have to check it.
Okay, thank you.
Welcome.
So, well, my question is about this integral. So in the formula, you have an integral over t and x.
That's right.
So what does this mean? So on only a very small region of t and
yeah,
x?
so this region, the size of the region depends on the size of your experiment. So it's like if you have a facility of detecting particles coming out of a vacuum, so you have a finite size laboratory and you keep watching for a certain period of time, then you do the integral within that region. So in our calculation, we checked various possibilities. If you keep them small, then of course it's easy, right? You just take the value of C at that point. If you take it large, there is some cancellation, but note that C inverse is an exponential factor. So when you integrate the region far off from the region where you have maximal value of C inverse, they don't contribute. So essentially only the region may be of size 1 over omega with the largest value of C inverse. That's the region where you dominate. That the integral dominates by that region. Yeah, so we also considered, for example, the case when the integration includes the region inside the matter. If you consider a thin shell, in that case, as an example, you know what is the geometry inside the thin shell, and then you can do the computation. But anyway, so in general, without special reason, this is not zero, so that with a sufficiently large value of C inverse, you get a large number.
I see. I see.
So is this the omega, which is finite?
Yes.
Is a finite to which observer?
This is to the distant observer. So this is the Hawking radiation dominant frequency. So it's of order 1 over A.
Right. So, I mean, if it is finite to infinite observer, right? Then it should be redshifted from the infinite frequency near horizon.
Yeah, that's right. So basically C inverse is the redshift factor or the blue shift factor.
Right. So that's basically what seems to be going on.
That's right. That's right. So this is essentially not too different from the old Transplanckian problem. It's just that I actually considered an invariant quantity so that you cannot dismiss the Transplanckian problem by Lorentz boost, and then actually consider a transition amplitude, which you must admit that it's within the validity of the effective field theory whenever you assume Hawking radiation. So if you do not assume Hawking radiation, if you claim that this state doesn't exist in your effective field theory, then you are also saying that your effective field theory doesn't really predict Hawking radiation. So this is the minimal resolution I was trying to talk about in the first lecture. So when you assume Hawking radiation, only then you need to say your effective field theory predicts high energy events. So it's basically pointing out the incompatibility between Hawking radiation and uneventful horizon in the effective field theory over a length scale beyond scrambling time.
Excuse me?
Yes.
Yes, so usually in this near horizon region, this particular description might be not good for this distance observer. So I mean, it's not so clear whether this particle really around the near horizon. This so
yeah, so that's why I didn't.
That is not. Oh, sorry. Go ahead.
Yeah. So indeed, so that's why I did not talk about an arbitrary particle state. I'm restricted to this particle state, which you have to include in the theory because you want to make a claim about Hawking radiation. And this particle state, which has an arbitrarily low energy. So I'm only including the states which, if you do not include, you are also excluding Hawking radiation prediction. And then I'm also fine because without Hawking radiation, you don't have information loss paradox.
But so yeah, my confusion is so so for distance observer, so this he may observe these particles, but in so where this particle come from is not so clear, right? In the near horizon region, or some people claim it's around twice or
oh, you're talking about right. So that is about the usual Hawking radiation.
Yeah. So if there's some, so that I'm a bit confused about so this the interaction between this Hawking particle and some other particular other issues. So what is what kind of process is enhanced in your?
Right. So I'm considering the process, the transition from en-route vacuum to an excited state, which a priori has nothing to do with Hawking radiation.
Okay.
So I'm just considering transition from en-route vacuum, no particle state, to some state with particles.
Many particles,
right.
So you're saying
if I consider an arbitrary particle state, you can say that, okay, this state is not included in the effective field theory. So I consider the state which has to be included in the effective field theory. But this is not a Hawking radiation particle.
Oh, okay.
Yeah, this is not. This is created by higher derivative interactions.
Okay, thanks.
You're welcome. So other questions? So I should finish my talk. Of course, all these quantities are invariant, so it may be of interest to see what happens in the capital U, capital V coordinates in which the metric actually is of order 1. In terms of that coordinate system, what you see is just that the corresponding frequency in terms of the capital UV coordinates is very large. It's the Transplanckian problem people talked about, but here you just have an invariant quantity. So it's saying that, of course, you may say that, well, I shouldn't consider, frequency so large. You might say that before you get a very large invariant quantity, the effective theory should become invalid. But before that, there would already be particle creation. So what happened is just that equivalence principle is violated by higher derivative interactions. This is known in the past. Equivalence principle only works for second derivative equations of motion. When you have higher derivative interactions, equivalence principle is violated. There is an example of this for the coupling between electromagnetic waves and gravity by Lafrance and Myers, in which they demonstrated this also. But I think this is, in general, this statement is known before, although I don't know who to cite for this. So basically, we have the ingoing active energy, which gives you a V dependence in the background geometry. And then the higher derivative interactions breaks equivalence principle, allowing you to evolve from the vacuum state to a non-vacuum state. And so the conventional model, in some sense, it's indeed consistent, because if you consider an effective field theory in which all the higher derivative interactions have extremely tiny or zero coefficients, if the coupling constants of all the higher derivative terms vanish, then you are fine. But in general, when you have some of these higher derivative interactions, then because they break equivalence principle, so vacuum can be evolved to non-vacuum, and eventually you get effective field theory breaking down, and you would depend on the UV theory. So the implication is that Hawking radiation, uneventful horizon, they cannot be compatible for a period of time longer than the scrambling time. And after the scrambling time, effective field theory is no longer reliable. And depending on the UV theory, two possible situation is either Hawking radiation stops or Hawking radiation continues, but with firewall. These are two possibilities in which you don't have information loss paradox. You could have a UV theory. I mean, I didn't prove it, that it's impossible to have a UV theory in which you have still Hawking radiation, but no firewall. I cannot prove that because I don't have a complete list of UV theories. I just proved that the effective field theory is no longer valid. But yeah, so, but that's not the problem within the effective field theory description. Finally, let me make a comment about Einstein equivalence principle. Strictly speaking, Einstein's original proposal of the equivalence principle is restricted to non-gravitational part of the experiment. If you have a vacuum expectation value of the energy momentum tensor, which is very large, since the vacuum energy momentum tensor can only be measured gravitationally if it doesn't come with particles. So actually, strictly speaking, it's not excluded by Einstein's equivalence principle to have a larger and larger vacuum energy momentum tensor. And once you have a large vacuum energy momentum tensor, you have a large curvature and you are allowed to have a large outgoing flux of particles. So actually in the end, you may not really say that you are violating Einstein's equivalence principle. Let me also comment that because of this, you can actually imagine low energy effective theories in which you do not start with the uneventful horizon assumption. You assume some other assumptions such as TUU larger than 0 around the horizon, like in the KMY model, and then you actually could get a consistent picture. So to conclude, we have shown the incompatibility between Hawking radiation and uneventful horizon, and also that the effective field theory eventually becomes unreliable after scrambling time, actually within the scrambling time. So I hope you are convinced that the information loss paradox is alleviated, to say the least. Thank you.
Thank you very much, Pei-Ming, for a beautiful lecture. Yes, so we have a question session. So do you have any question? Would you please?
I have one question.
Please.
So are there any full is it possible to, are there any numerical results? I mean, at least as far as, in my opinion, at least in two-dimensional models, I mean, classical, background geometry with the quantum fluctuating bosonic mode, one may perform some numerical calculation in a fully self-consistent way. Are there, or there are any difficulties to perform that?
There are analytic, but perturbative calculations. So, I mean, we can compute this transition amplitude.
And what I'm saying is full numerical calculation. Computation, yeah.
Numerical calculation.
Yeah, I mean, Einstein equation, but if you formally integrate out matter fields and some logarithm modification, so yeah, such a thing. I mean, solving the equation. You know,
we haven't done that. That's right. We haven't done that. but that would require some knowledge about the coefficients, right? The coefficients of all these higher derivative interactions. So actually there could be several different classes of possibilities depending on how fast the coupling constants go to zero when you go to higher and higher derivatives. Yeah, in the 2D simulation, they didn't consider the higher derivative interactions, right? So I wouldn't say that's fully, consistent with this.
I mean, even for, without any interaction, just, method is free Gaussian model on a background. But if you, are
Sorry?
there any, without any interaction, just solve fully self-consistent way, within the assumption of classical geometry, are there any results for this?
Yeah, sure. There are a lot of numerical simulations.
So what was that related to this?
You mean for the conventional model?
Yes, yes.
Oh yeah, so the first one people quote is the one by Parentani and Perrin. So actually there they have already confirmed this picture. So you have this Parentani-Perrin paper in '94. Afterwards, some of them also have other collaborations in which they have more simulations. And there are many other groups also have simulations. Without a higher derivative interaction or any interaction, just free field theory coupled to gravity using, say, the 2D model of Davis falling error rule and so on. Yeah.
This is the result. I see.
Yeah.
I see. Thank you.
You're welcome.
Other question?
I have one question. In your effective field action, you have lambda 1, lambda 2, and lambda 3. So what's the origin, physical origin of this coupling terms?
They are just low energy effective terms arising from a generic UV theory. So you have a UV theory and then you go to low energies, you get these effective interactions. So in general, you have infinitely many terms. And when you go to higher and higher energies, these higher order terms would become more and more important. So this is, I guess, now the standard view about effective field theory nowadays.
Okay, thank you.
Thank you.
Other question?
Yeah, can I ask one?
Yes.
So did I understand correctly that, so the effect, so these large higher derivative terms, they become large, like, whenever you start from whenever you relax basically the Schwarzschild approximation. Is that correct? So if you start with some kind of, so if you start with some kind of time-dependent solution before like the apparent horizon, then you always get this kind of large higher derivative terms. Is that correct?
Yeah, something like that. As long as you don't have other, symmetry to give you conservation laws. So in general, without conservation laws, in general, you get these large quantities.
Right. So in particular, for example, if you consider this Vaidia, like, with some kind of like this ramp, right? This time dependent, that would also give you the same.
That's right. So actually, ingoing Vaidia metric is completely compatible with the near horizon geometry solution we obtained.
Mm-hmm. Thank you.
Thank you.
Other question?
I have a question. So without introducing these higher derivative couplings, you will not see any problem. Is this correct?
Yeah, I didn't see any problem without the higher derivative terms.
So the maybe information just lost or this bug would be
Yeah, so, but I guess we should not imagine a theory without these terms, right? Just like, so there was a slide that I went over very quickly. I realized that I shouldn't have those effects. Those slow me down tremendously when I go over the pages. So, right, so UV theory, we know that, for example, it cannot have global symmetry. Otherwise, it's just impossible to resolve the information loss paradox. So here I'm adding a tiny, very weak constraint, that is, you have to have higher derivative interactions.
Hello, Pei-Ming.
Hi.
Yeah, right. Again, one final question about the higher derivative. So, if there is any covariant object which is finite at the horizon or near horizon, then, as you say, those will be very important. But let's think about the no-hair theorem, and which is saying that basically it is almost saying that the black hole doesn't have much shape, which means that it looks like to me that it is more or less equivalent that any derivative parallel to the horizon direction is a kind of a zero or vanishing very fast. So probably it may be not easy to establish the fact that higher derivative or any derivative is meaningfully finite near the horizon. Yeah, that is my comment.
Well, the no-hair theorem, I think it's only proven for certain theories, right? Not for generic theories. If you add higher derivative terms, I guess. Yeah, that's right. That's an interesting question. So maybe
there is a Hawking radiation or any hair, right? If there is any object derivative or Hawking radiation which is already finite, very near horizon, then all those are very important. Yeah, I don't want to discuss any more about this finiteness of the Hawking radiation, but I mean about the higher derivative is also the same, almost the same fate. So we need to establish actually whether there can be any finite, I mean, derivative or higher derivative near the horizon. Because everything is very easily washed out near the horizon. So this is just almost a very well-shaped or very nice. Maybe that's the beauty and also dryness of the universe near the horizon.
Okay. Yeah, you're making a comment. I have nothing to answer, right?
Yeah.
Okay. Just want to make sure.
Easy to have a really finite quantity near the horizon.
Other question?
I have another question. So this, you might know this supersonic Hawking radiation occurs in some fluid, and in that case, the mechanism of Hawking radiation is very similar. But so suppose our UV theory at Planck scale has higher derivative, but I cannot imagine it can affect this acoustic Hawking radiation phenomena. But so what is the difference between this supersonic black hole and this real black hole?
Well, in some of the experiments, I'm not following closely those experiments in the early days.
I'm not sure whether this is really realized, but suppose, yeah, but I don't know. But anyway, so what's the difference?
What is the difference?
Yeah, I mean, as a
In
theoretical
principle,
viewpoint.
it's the same, right? So there
Yes, the
they
same,
also
so-
have effective theory, which is actually no
some
longer valid, right?
hydrodynamics and
no longer valid. So then they say if their claim is correct, that they really see something like Hawking radiation, then I guess what I'm saying is that before that, they should have seen something unusual around their horizon.
I
So
mean, due
maybe,
to the UV physics, like string theory, or
well, they have a better theory, right?
maybe standard model, or
right. Standard.
But standard model is not higher derivative, so yeah.
Right.
So yeah, so in that sense, so it's not so clear for the real. It's not so clear for me whether really this UV affect this kind of low energy phenomena. So
Yeah, I'm not saying that, right. So as long as you accept that effective field theory is no longer reliable, then I have nothing to say, right? Because I don't know what is the UV.
Oh yeah, that may be true.
Then it's a case by case problem. So
but so your point is, so due to this UV theory, the description would be break, but so we have to know UV theory, right?
Right,
Even
you have
in
to
this
know
hydrodynamics case. So
that's right.
that is very counterintuitive. So and yes, so that is my impression. So if you have any good answer, it'll be good. So,
yeah, no. So yeah, I don't know. So as I was saying,
yeah.
logically, it's possible that your UV theory would give you a Hawking radiation without firewall, because I don't know anything about UV theory. So in principle, that's a logical possibility.
Yeah.
But if you want to say that information is preserved, we do not really rule out that possibility by the effective field theory. So I'm only giving this much. I don't really know. So yeah, but that's a good question. So maybe we should take those experiments more seriously.
Yeah.
Sorry, I seem to suggest that I didn't take them seriously, but no, I took them seriously all the time.
Yeah. Thanks.
Okay, other question? So before closing this session, let me ask a final question. So you have been talking about this information loss. And so suppose I can actually detect this high energy modes, then actually information loss can be retrieved by collecting all of those high energy modes.
Right. So you mean before the effective field theory breaks down, you have some high energy particles, so you can bring out some information of the collapsed matter. But afterwards, maybe Hawking radiation stops, and then there is no need to bring out all the information. You just get a classical black hole.
Mm-hmm. So before this stopping point, you collect all the high energy modes. So it's not just Hawking radiation. It's Hawking radiation plus some high energy modes.
That's right.
So it's not thermal. So that's how information loss.
That's right.
I see. Okay, great. Thank you very much.
Thank you.
So, yeah, thank you very much for very nice lectures. And let's thank Pei-Ming again here.
Thank you.
Thank you very much.
Pei-Ming, thank you for joining us.
Thank you.
Bye.
Bye.
Okay, so we shall go to the break for 10 minutes. Then the next session will start at 5 p.m. Thank you very much. So Pei-Ming, thank you very much.
You're welcome. Thank you.
Do you have any comments on islands?
Islands. Yeah, actually, it's interesting that I saw in your work that you also get a scrambling time, right?
Yeah, in fact, there is something which is very close to the horizon.
Right.
That's the edge of the islands. And
Right.
the distance, well, in the ordinary R coordinate is just Planck to the fourth or something.
Yeah, so there's some similarity. So in this picture, actually, anything that's too deep, actually, it doesn't have to be very deep, but just a little bit under the surface of the collapsing matter, everything's frozen because of the tiny conformal factor. So if you think those frozen degrees of freedom actually should be, discounted or, treated differently, maybe that's the island. So I don't know.
That's interesting. Do you know the this lowest power of L Planck as a kind of distance scale, or the radial position of this violation of the inequality happens?
Sorry, which inequality?
So in our results of islands computation, the islands appears very close to the horizon, and in the R coordinate, it goes like Planck length to the fourth. And I'm wondering this power can be somewhat seen in your approach.
I see.
So your result actually depends on what kind of higher derivative terms you assume, right? Suppose I take the lowest higher derivative, then
it actually depends on many things. But if what I said was relevant, maybe it's not the higher derivative, but the but like how much inside everything's frozen. So you have a time scale of evaporation, which is a cubed over Planck length squared. So if the conformal factor is much much smaller than the inverse of what? Planck length over Schwarzschild radius squared, then everything can be considered frozen inside, right? So that is corresponding to a certain point outside the trapping horizon. So I'm not sure if it's possible to make connection in that way. Yeah. But supposedly, if the holographic picture is right, then the higher derivative effect is already taken care of, right? So the question is just what island corresponds to physically.
Yeah. Yeah, in any case, so in any island computation, there is no dynamical evolution of space-time.
Right.
So the direct connection to your story is not seen.
Yeah, so that's actually a very interesting question. It would be great if we can make some connection.
Sure.
Yeah,
okay.
Yeah, thank you.
Thank you. It was very nice. Yeah, I learned a lot, and yeah, your story is fascinating. So I hope
Thank you very much
for the success of your story.
Yeah, let's keep in touch.
Yes.